Okay, welcome. Good morning. My name is Ella Metlenko. I'm here to chair this lecture for today. I'm the Director of Research and Product Development, which is within the Digital Earth Australia branch, focusing sort of on the area of Australia, developing theme-based products in the coastal, which you'll hear Steve talk about today, but also in the hazard space. Some of you might have heard of DA hotspots, and in the terrestrial land cover product, and also our inland water team, which is currently working on developing a national wetlands inventory product. We also look at calibration validation of our products at the analysis ready level 1 and right down to the level 2, such as things as water bodies and various other classes that we're extracting from Earth observation data. So I'd like to begin with acknowledgement to country. So I acknowledge the traditional owners and custodians of the land that we're meeting on today, which is the Ngunnawal and Ngambri people. I pay my respects to the elders past, present and emerging, but I also like to add that Geoscience Australia values the lands, water and sky as we work to deepen a shared understanding of country and earth. We respect First Nations people and their enduring connection, contribution, obligation and obligations to country. Reflecting on our shared history, we are committed to listening and learning. So welcome. The Distinguished Geoscience Australia lecture series, affectionately known as DGAL, are a series of presentations nominated by Geoscience Australia staff, a prestigious recognition of their major achievements and contributions to earth science. So this week we are also celebrating National Science Week. It's a week to inspire everyone and a platform to celebrate the achievements and contributions of Australian scientists and researchers. So what better way to celebrate National Science Week than having with Dr. Stephen Sagar and our audience here from our Space Division, who will share with us how Earth observation from space are being used to monitor the Australian coastal and our intertidal regions. Stephen Sagar has led the coastal team with the Digital Earth Australia program since 2015, with a focus on providing open source Earth observation EO products and tools for historical characterisation and ongoing monitoring of the Australian coast. He has worked in many iterations in the remote sensing branch, within Geoscience Australia since 2007, and has had part of its development from a data provider to a leader in the Earth observation science, both nationally and internationally. Steve has a background and a PhD in shallow water remote sensing applications and has led the coastal team through the release of a number of foundational coastal Earth observation products, including our Digital Earth Australia coastlines and our intertidal suite, which you'll hear more about today. Please join me in welcoming Steve on stage, and we'll come back to any Q&A session after his presentation. Thanks, Steve.
Thank you. Thank you, Ella. Excited to be able to do this presentation as part of National Science Week. It's a really great opportunity for me to get some of the work that my team has been working on for quite a long time. I've been really lucky within Digital Earth Australia. I've had my team together now for coming up on 10 years, which sometimes is unique. You get a lot of shifting people through these teams, and it's given us the opportunity to really dive into some of these core research questions. So we're going to be talking about monitoring Australia's coast from space. We've got a complex environment to look at and talking about how we utilise Earth observation data to do that. And I've listed my team here, and it's no exaggeration to say that if it wasn't for the impressive work that these guys have put in over these years, I'd have nothing to present here. So I'm very much a vehicle to putting forward this work on behalf of the team. So a lot of kudos to that team. Let's get started. All right. So what are we going to talk about today? So monitoring Australia's coastlines from space. Why is Earth observation so well suited to play a leading role? And essentially also dipping back into time a bit and talking about why GA has been really fundamental in setting up this foundation so we can make this contribution. I'm going to talk a little bit about some of our core products and really look at the concepts that underpin what we do to be able to do this at a continental scale. And demonstrate what we like to talk about in terms of how these products are complementary in nature, not both in how they interact with themselves, between the two different products, but also how they tackle this complexity of the coastal region alongside other monitoring type efforts. And then highlight how these types of approaches have been really successful in getting uptake and use cases across different areas of government and industry. I wanted to make another acknowledgement as well too here. It was a little clumsily done, I think, but I really wanted to pull out the fact that our collaborators and stakeholders are key to these efforts. We've made a conscious effort within our team, especially to pull these stakeholders into the process as we're developing these products. And as a result of that, they've become some of our most valuable advocates. And it's really started to blur that line between a stakeholder and a collaborator. And that's been strengthened by the fact that we have a real focus on open source data and methods. And it helps us to then bridge the gap between what we are, which is Earth observation scientists, and coastal scientists. And I don't think any of my team would be offended if I said we're not coastal scientists by training, is we're really coastal scientists through osmosis of working with Earth observation. And having those relationships with these stakeholders and collaborations is what makes sure that the products we develop in this space are actually valid and are actually useful in this coastal science space. So to step back and talk about our coastline, we could get into an argument for an eon about how long our coastline is. This is a classical fractal problem. How do you survey a coastline? But it's big. We've put a number here that we use, 33,000 kilometres. But the point is, this is a big place. We have a huge country, we have a huge coastline to monitor, and it encompasses such a range of environments. We have anything from macrotidal tidal areas up in the north, tropical mangrove, wetlands. We have microtidal rocky shorelines. Anything you can imagine, we pretty much have to deal with in Australia at scale. More than 80% of Australians live on the coast. That happens in a lot of countries, but we've got such a big coastline that this means that a large proportion of our coast, even though we are on the coastline, much of our coastline is isolated and remote, notwithstanding. And these coastlines are dominated both by wave processes and tidal processes. So we have tidal ranges of anywhere up to 12 metres up in the north of the country, macrotidal ranges, right down to less than 1 metre in some of the rocky shorelines in the south. So putting all of those, the issue of remoteness, inaccessibility, the complexity of our coastlines, this means monitoring this at scale becomes a very complex problem, and there's significant challenges to be able to do this effectively and then have that flow on to management of the coastline. So currently, and in the past, there are a number of methods, obviously, for surveying and monitoring the coastline, and all of these try to deal with this challenge of cost and scale. So we can have anything from stuff taking place on aerial, on flights, things from aerial photogrammetry, and LiDAR. For example, the West Australian Department of Transport has a great program that measures shorelines, flying photogrammetry periodically. We can use in situ methods like fixed cameras and citizen science. Now, this is a couple of images I've put here, which is work that's really been pioneered through the University of New South Wales. We have a really cool program there where you can actually go out as a citizen with a camera, put it onto a fixed station and take an image of a coastline or a beach, as you can see here, and actually contribute through to coastal monitoring in a really sort of structured way. Drones are becoming, as they are across all scientific applications for validation and monitoring, becoming a much bigger part of this picture. And of course, we have sort of traditional surveying monitoring, going out with GPS and more traditional surveying methods. And some of these programs have been running in beaches across Australia for close on 50 years, so they're a really valuable resource. But all of these, the common theme to this is they all challenge to scale up. Like, these things cost money. It's hard to do them on a regular and repeatable basis at a continental scale. And this has been acknowledged. There's a new initiative at the moment that's been launched called the Coastal Research Infrastructure through NCRIS, and that aims to address this limitation that it's hard to coordinate these activities. But the challenges remain: cost, remoteness, inaccessibility. And really, Earth observation is being increasingly recognised and has been for some time. as a key and a complementary tool to these techniques. Now, this is in terms of scalability, being able to scale it up to the country, cost effectiveness, and the ability to be able to repeat these measurements, so repeatability. So I don't want to dwell too long on this, but everyone knows what Earth observation is, even if they don't know what it is, because at the moment it's ubiquitous. You can go onto Google Maps, you're seeing Earth observation data. Now, this has changed over the last 10 years significantly, and there are hundreds of Earth observation satellites that we could use for coastal applications. So I guess the question then becomes, how do we make a choice as to what data we use? And there's some classical trade-offs that, even though we have this many satellites and these lines are starting to blur with technology, that still apply. So we might want to think about what the spatial resolution of the data is. How much detail do we need to actually retrieve for the application we're looking at? We need to think about the temporal resolution. So what's the frequency we need to actually look at this location to get the information we want? And importantly, and this is where the differentiation between what people might think an image is and what Earth observation data is what is the spectral resolution? So how much information content do we have in the data? So even if you've seen an Earth observation image, like the one on the left here, the higher resolution one, on Google Maps, for example, most of the time you're looking at that in true colour. And so that's an RGB, it looks like a photograph. But the most important thing for us in many applications for Earth observation is the data that we actually get from Earth observation data that goes beyond the visible. So stepping into the near infrared and the shortwave infrared. So we had to look at another kind of change of resolution. So we've now changed from this high resolution commercial imagery to our old favourite Landsat. And you can see one of our, I think this one's Landsat 8 up in the picture here. This is now to 30 metre resolution. Of course, you lose a lot of detail. But being able to use these different bands, so this is looking at a very simple remote sensing process, deriving an index, looking at water, where we utilise data in the shortwave infrared and data in the visible, we can start doing much more powerful things. Now, as I said, these sort of distinctions are starting to blur, so why would you still use lower resolution data if you could use high resolution commercial data that revisits the same place? Because increasingly we're looking to other criteria to work out what's suitable for doing these applications. So we're looking at how fast you can get that data, what's the accessibility like, can we get it from different platforms in an easy way? What's the cost that's going to be incurred, and licensing? If we need to monitor a country the size of Australia with commercial data and we have to pay for it, that's going to impact that scalability and the actual long-term use that we can achieve with limited funding. And what is the processing infrastructure requirement? So higher resolution data, more compute, more data storage. And there's also been a massive shift towards having analysis-ready data where you can get that data easily. You don't have to do pre-processing and you can actually work on that data as it is. And do you want to use a sensor that's highly calibrated over time, something that's been studied, worked through for decades, or are you happy using experimental CubeSats? So all of these kind of criteria are really important to consider now when we're talking about doing a sustainable EO monitoring program. Because we need lots of data. Coastlines are dynamic. I pulled out a couple. I sort of went searching recently because there's always news stories about erosion and impacts on coastlines. And I only had to go back a couple of months to pull out some of these to look at how these coastlines are changing over time. And then we have impact stories such as Cyclone Alfred that we had up that devastated some Gold Coast beaches. We've had things like the Bribie Island breakthrough. So a lot of these things are quite high profile, but this just serves to highlight that these places are really dynamic, whether it's through natural processes, these kind of event-driven impacts, or whether it's just through human intervention. Because we live on the coast, we're always managing that coast to prevent to protect our infrastructure, and this has impacts to how the coastline changes across the scale. And of course, growing pressures from climate change. And doing this with this high resolution commercial imagery is just not feasible, it's cost prohibitive. And at the same time, there's been this increasing drive from government to be able to report on things at a continental scale. And often this is because they've started to recognise the ability of Earth observation to provide that kind of information. And a lot of that has to do with the work that Geoscience Australia has done over the last decade. We've really positioned ourselves as leaders in processing this data at scale and managing it, and it's put us in a really strong position to really effectively meet some of these monitoring needs. So we're going to go back in time a little bit and actually see how we got there. And this one was for you, Lars. So we're not going back in DeLorean timescales, we're just going back to 2008, which is actually interesting because stuff has moved so quickly. You think it's a long time, then when you really think about the scale of change, it's not such a long time. Probably the key moment that came about in 2008, the USGS, which is sort of our counterpoint in the US, Geological Survey, actually made the Landsat archive free. So this is decades worth of Earth observation data. Previously you had to pay for this data in the same way you pay for commercial data. So now we had decades of data. And Geoscience Australia has always been a partner with the Landsat program, so we've been acquiring data since the 1980s, but it meant that this data was sitting in old magnetic tapes, literally in the basement. So in 2011, there was an Unlocking the Landsat Archive initiative launched with the aim of taking this resource, which was now free and available, and providing it out to the public. And we did that via the National Computational Infrastructure. Having this on a computational infrastructure like that and cloud and different ways of doing high performance computing meant that this led to the development of the Earth Observation Data Cube concept. Now, simply put, the Earth Observation Data Cube concept is fundamentally looking at having pre-processed analysis-ready data, ready to use, and being able to query that data effectively, not only through space, but through time as well too. So you can actually then, this opens up a whole different dimension of how you can actually scale this data and look at it in an effective way. So in 2015, and I made a best guess at this date, this was kind of an organic process. The Australian Geoscience Data Cube was formed in collaboration with some of our scientific partners like CSIRO, and it's evolved into what we have now today in Digital Earth Australia. Since then, we've incorporated a bunch of other data sets, including Sentinel-2 from the European Space Agency, and this means we're offering free and open data across the country at revisit times of approximately 2 to 5 days. So anywhere in the country is being imaged constantly and provided. We manage over 9 petabytes of data, which I can't even think about how many zeros that is. Going back to 1986, we now do it via Amazon Web Services, and the new data we acquire is being provided in near real time. So from the moment that satellite observes a spot in the country, we're providing that data out in about 24 hours. So thinking back to the way we used to work, and I didn't even go back further to when we would, buy a scene, get a CD-ROM, put it in your machine and work on that. Things have changed so significantly that it's really hard to imagine it's happening in such a short time. But there are still challenges. So before you have analysis-ready data, this is what you get when you get a time series of data. And if you're looking to try and work out what's changed in this image, good luck, because you've got inconsistencies from atmospheric effects. You might have things like geometric alignment and accuracy that you need to account for, terrain variation. So depending on where the sun was and where the satellite was, you'll get shadows, and you've got clouds. So being able to separate out from data the actual change you want, as opposed to the noise in the data, is still a challenge. And this is where the concept of analysis-ready data comes in. So this process enables us to do a whole bunch of different types of scientific corrections to remove that atmospheric effect, take out that terrain illumination, put metadata into there to describe when we do have good geometric alignment, so you can filter for that. And you can see the information you can now glean from this same data being processed in this way and being provided with this analysis ready is so much more impactful, and you can actually glean so much more information from it. We have these same challenges in the coastal zone. So we'll have clouds, we'll actually have other things like glint, we'll have atmospheric events, we'll have terrain effects on the coastline that we need to deal with. Now, of course, analysis-ready data is going to help us with that, but it quickly became apparent when we're looking at monitoring where we have one more challenging variable that we need to account for in the coastal zone, and that's tides. So this varies across the country in scale and effect. In this image here, we've got an 8-metre tide. So you can see as you step through time, if you're actually looking to see how this coastline changes, so to speak, you have to isolate that, or you have to be able to manage that in an effective way to isolate the changes that you want to see. So we quickly talk about tides in Australia. So this is a really nice hypnotic image that you can look, so don't stare too long, but tidal regimes, they vary. So we talked about having a macrotidal range in the north, 10 plus metres, microtidal in the south. We have a range of different types of phases, whether you have 2 low tides, high tides a day, and these vary in a temporal and a spatial context in, let's just say, not a very even way. And being able to monitor them and characterise them going back in time is a challenge. The tidal gauge network we have in Australia is too sparse to do that on a continental basis. It's, logically, it's centred around population centres, and you often have incomplete data, so some tidal gauges, mightn't be maintained, they might have been established at different times, so you can't go back in time consistently to be able to comprehensively characterise the variation that we need. So this is where global tide models come in. Luckily for us, this is one of the most regular and repeatable processes that can be modelled. So you can do that mathematically if you have the right underpinning data sets, and many global ocean tide models have been developed that can actually go through and enable us to predict and to retrospectively look at what a tidal height was at any point in space and time. Now, theoretically, this is the perfect input to coastal remote sensing. So we can match that up with a satellite data array. So we've got our time and space in the data cube. We can match it up with a tidal height array, and it starts to enable us to get a handle on what's going on in the coastal zone in terms of tides. And fundamentally, this is the key concept that underpins our group. The insights we got from this, and we've been leaders in integrating this EO data and global tide modelling and seeing what we can then get out of this information. So the real concept is a reframing. So we think about querying things through time. We want to reframe that so we can also query things based on tide. And we do that by tagging each pixel in our time series, in our satellite data, by tide. Now, if you think about the scale that we're working here, if we're talking 10 metre pixels in Sentinel-2, going around the country, going through, that's a lot of pixels. So we now have approaches, we have models where we can actually go in and optimise for every pixel when it's acquired, when it's passed over by the satellite, optimising all of the global tide models available, working out which is the best one and assigning a pixel. So if you look at this conceptual diagram here with a tidal range or cycle, you can see the tidal cycle in the model tidal cycle in blue. Each of those observations in black is when that pixel has been observed at a certain tidal height. So over, I think we've got about 4 years there, you can see all of the observations and have them tagged. And what that then means is we've moved from that noisy data to data that we can essentially control. We can actually use that data and order that in a pixel basis to actually isolate, control, work out how we visualise, work out the kind of interpretation we want to make on that data. So it's put us in a really powerful position. So we can look at things like, instead of subsetting data based on time, we can subset based on tide. So if we were to look at a pixel or images through time here, and we wanted to just extract some high tide observations from a certain epoch, we can create a high tide composite from that. And this has the benefit of then isolating all of the other low tide and that noise, that tidal noise. Similarly, we can do something at low tide and create a low tide composite. Now, there's so many different ways we can slice and dice the data. Doing a lot of this research into the way tides interact with EO data actually brought us into another area that we hadn't expected to have to deal with. And people that are observant looking at this graph might notice something. There are only low tides at this location in summer, and there are only high tides in winter, as far as the satellite is concerned. So when you're going over with that satellite, you're never actually picking up low tide in winter at this location. We thought this was kind of weird. Proves out it's something. So essentially what this means is the assumption was, if you're looking at a long time series images with a sun synchronous sensor, so when I say sun synchronous, I'm talking about Landsat and Sentinel-2, they orbit the Earth and they acquire at the same time, at the same location, every time they acquire data, give or take. The assumption was in coastal remote sensing, if you image an area for long enough, you'll pretty much get all the tides. You'll characterise everything, you're safe to map everything. It became really clear to us very early that this simply wasn't the case. So if you look at the second panel down here, halfway down, you can see this is an area in northern Queensland that these are images of Landsat over 30 years. You've observed that area for 30 years with that sensor and you have never seen a low tide, and you never will. Similarly, down in South Australia here, imaged for 30 years, you never see a high tide. Now, it even went a step further. We started to do some theoretical work in San Francisco with some of our partners, and we're looking at a theoretical bias in their data. They never actually see a low tide over summer with Landsat or Sentinel. So I guess this poses a esoteric question. What does it mean for EO products and the products that you're doing if a satellite never sees low tide over summer? If you're doing a habitat map or something like that with certain sensors, what does that mean? I don't have an answer for what that means, but what I do know is that we actually have to consider that when we're designing a product. So now we're going to start talking about the actual products, and I'll have some prettier pictures, so not so much about tides. And we needed to think about, if we're going to design a product, we had an aim of doing a coastline monitoring product that we can repeatedly and consistently map coastline positions going back in time and on an ongoing basis. So knowing what we know about EO data and tides, we knew that we couldn't do a continental application using single images because obviously things acquire at different times, different conditions. So the focus became on doing annual median products. The tidal bias meant that we couldn't focus at low and high tide just because with certain the sensors we needed to use, we couldn't actually use that consistently around the country, so the focus was on a mean sea level product. So where we ended up at was doing an annual product, which is aimed at reflecting median change trends over time. Now, we distinguish that intentionally against a product that might pick up instantaneous impacts. So, for For example, a product that might be able to pick up after Cyclone Alfred has gone over, where is the shoreline now on the Gold Coast? You probably don't want to know because the shoreline's not in a position they're very happy with, but this is not what our product does. And we'll sort of tease through that distinction a little bit later on. So very quickly, the way we apply this using our pixel-based attribution, we showed before that we can subset data based on high and low tide. In this instance, we subset our data in annual time steps around mean sea level. So going through, and as I said before, every pixel we attribute a tidal height to, and that enables us over an annual period to subset those pixels based on the ones that are centred around mean sea level. We can then use those pixels to create, and I said that was a simple process back before the water index, to create a composite of an MNDWI water index. And what that means is we've now got a very noise-free median indication of what is wet and what is dry in that location. And we use a sub-pixel extraction methodology. Definitely don't have time to go into methodology, and it seems a little bit magical, but I'll show that we've actually managed to achieve this with the validation. It means that we can actually pick out that water line at a higher resolution than the pixels and the data that we're using. Again, doesn't seem like it should work, but we'll show that it definitely does. So we end up having these shorelines, and this is our product. So this is a multi sort of scale product we have here. We're able to pick out rates of change at a continental scale, looking at coastal change hotspots. We start to be able to then drill down at every 30-metre spacing around the continent. We can pull out rates of change at these locations along with uncertainties. And we zoom right into sort of our finer scale product, which is the actual coastlines. We've got annual coastlines which document the median position of that coastline at mean sea level. So you can interpret this data in a number of different ways. These can apply to local applications through to continental sort of health checks of beach stability. Now, this is a median product, like I said, and how can that be applied? So it's actually quite useful to have it as a median product. There's a pro and a con. Often people come to us and ask whether we can map something that's just happened, and we simply can't do that. But what it does mean is that somewhat that noise of those event-based and high-frequency changes in coastline is averaged out or medianed out, that's probably more the accurate term. So what we're really able to then focus on are these longer term trends of coastal change. So we can really start, the noise comes out, we can really look at coastal change at a scale, looking at these erosional trends across the country and impacts. We can apply that to things like ecological applications. So the example here, we've been looking at a lot of migratory species, often with shorebirds, for example. This is a turtle nesting region up in the Northern Territory. We can start looking over the longer term, how those environments, those areas have changed, and whether or not management actions need to start to be taken. And we can also start looking at the impact of engineering and human interventions around the coast. So a lot of coastal engineering work takes place in terms of erosion mitigation, and we can start showing a historical picture of how they impact the coastline and help people then to plan those actions forward when they're looking to make these coastal engineering decisions. We've had some really nice collaboration internally in GA. So Dr. Rachel Nansen, who's actually listed as a co-author on this, because Rachel was involved very heavily with us developing our coastlines product. And this is an example of having an actual coastal scientist telling us where things work and where they don't. She was able to demonstrate how GA coastlines can capture these geomorphic trends and at a spatiotemporal scale, which has been really hard to do on an ongoing basis. And really perhaps even more impressively, tie back the 32-year history of coastlines back to really old historic geomorphic studies and show how that adds value to the assumptions made back in those older studies. And it's actually set the scene for a potential project that we're thinking about revising the National Coastal Risk Assessment, which is really, really exciting. The QR code there is for her paper because it is a great paper. I'm listed as a co-author, but I probably had very minimal to do with the cool graphics that she has in that paper, and it's definitely worth a read. So for people to have confidence in a product like this, they need to know that it's accurate. And this was probably one of our biggest validation campaigns that we've done for a DEA product thus far. And it really leveraged the fact that we have good relationships with our stakeholders, because we were provided with literally thousands of different kinds of data sets to validate this product, ranging from aerial photogrammetry, traditional surveying, drone measurements, you name it. They were all thrown into the mix. There is a conspicuous absence up in the northern part of the country, but we will get to that later as well too. Looking at the analysis, we were able to confidently say that these rates of change we're picking up were accurate to about 30 centimetres per year. Higher accuracy along macrotidal shorelines, lower in microtidal, and lower in the macrotidal sort of tidal areas. And again, we'll talk about why that is. On the left here is our subpixel. So what we've done here is we're looking at one of the beaches that have that long-term monitoring effort. This is Narrabeen in New South Wales, and they have about 50 years worth of data taken with in-situ surveying. What we've done is taken a transect through that data, because there's not a lot of actual beach movement here going on, and it varies. And you can see in the orange, that's our profile of our DEA coastlines, and we've matched up to the dark blue, which is the median of all of the survey observations taken over time. And we're very happy. We're picking up that median signal that they are surveying pretty accurately. But the most impressive part for us, and sort of a bit of a relief, was looking at that grey area in the graph, which hopefully you can see, but you can see the brackets, is the width of a Landsat pixel, and that's 30 metres. So you can actually see we're picking up the change within that Landsat pixel. So that subpixel methodology that we've employed is doing what it's meant to do, and we're picking up that subpixel change, which, you know, we were very relieved, because this is the core concept of what this work hangs on. But there's a value of having a repeatable and regularly updated set at scale as well too. So one of the things that we were involved in very early in the piece was providing beach stability statistics at a sort of a continental scale to the Department of Environment for State of the Environment reporting. And this means that being able to do this thing at scale, we can report on regional areas, we can report on a continental basis. And what came out of this was really quite surprising. Often the narrative around coastal change and erosion is often quite alarmist, because obviously there are impacts on infrastructure, there are impacts on housing. These are the kind of things that make the news for obvious reasons, and it's right that they do. We were able to show that the majority of our coastlines, probably about 70% varying year on year, are actually quite stable. And they vary over different years based on different things like climate pressures, climate indices. And this was actually picked up by Professor Andy Short, who's been one of the preeminent coastal scientists early in the piece, who's been one of our strongest advocates for this data, which was actually able to use these kind of insights to sort of push back on the narrative that Australia's beaches are just eroding, we're going to lose all our beaches. It's simply not the fact. The story is a lot more nuanced than that, and having this broad-scale data set enables us to really sort of make those arguments, but also on the other hand be able to drill down to these areas where impacts are an issue for people and for industry and things like that. But rarely is there a tool that works well. And so now we've headed up north, where we have little validation data and we have a lower accuracy. So I think one of the things that we've been very keen to do with a lot of our products is sort of wear our errors on our sleeve, so to speak, and acknowledging where things don't work. And so we've been very conscious in all of our products to incorporate uncertainties and making that very clear to the user. So in these mudflats, we get this kind of coastline. And you can see there in dashed lines, which means that we've been able to look, when the algorithm runs, we can tell that there's certain uncertainties in that process, which means that we're not confident of this shoreline. So we present that as a dashed line within our product to make sure people understand that. It's well described in the product description. If you think about a muddy intertidal flat, if you've ever sort of seen one, walked out on one, remnant water, it's mud. It's hard to delineate what's water, what's land. And the remote sensing signal in the satellite has the same difficulty. So being able to delineate a mean sea level shoreline through a muddy tidal flat, it's kind of not surprising when you think about it that it has trouble doing that. So we needed to start tackling the intertidal zone if we wanted to do comprehensive modelling. And luckily, this is actually where we started. So right when we started around this concept of matching up tidal data to Earth observation data, this is the first thing we did, is we started to look at how we could look at modelling the intertidal zone. We released a National Intertidal Digital Elevation Model back in 2018, and it played a really good role of bridging that gap between topographic elevation data and bathymetric elevation data, but it had its limitations. So it was low resolution, 25 metres, our old Landsat resolution. It was static. The methods we had for doing this required about 30 years of data, and as we've already talked about, having a 30-year median model doesn't do a lot for dynamic areas, so we actually had to mask them out. So it wasn't very good for monitoring things. And it was based on interpolation, so we lost a lot of detail through these complex zones. So we needed to shift this sort of method that we'd now developed for doing pixel-based attribution into the intertidal zone. And this is how we do it. So I'm going to ask you to imagine you're looking down. This is a tidal flat, which is a very steep tidal flat for demonstration purposes. You're looking down at a particular pixel where the star is, and you're looking up at a tidal cycle up there. So we're currently at low tide and we're looking at this pixel. It's dry. The tide comes up, pixel's still dry. You've got another satellite acquisition where you've got a dry pixel. At some point, this pixel's going to transition from wet to dry on that tidal cycle, and as the tide goes up, it stays wet. So if we're to sort of visualise that in respect to satellite observations through time, you can see the increasing wetness on the y-axis and the tide on the right, and you can see as the tide goes up, you get an increasing wetness at that pixel. Now, we've already looked at the fact that we can quantify that wetness with remote sensing data, so we can look at that using a water index, which means at some point, as that pixel transitions from wet to dry, there's a sort of inflection point where we can infer what the actual height was based on the tidal height of that pixel when it became wet. And we can do that for every pixel. We can do that for Landsat and Sentinel-2. So we've now got 3 years of data. We model this on the 3 years centered around the year of interest. We can have a tidal height array, we can use every global tidal model that we have in our toolkit, and we can optimize that and assign the best tidal height to every pixel in that array. So essentially, at every pixel, we're doing this process. Wherever we are in the intertidal zone, we're looking at how that pixel transitions from dry to wet. Yeah, that makes more sense. With that inflection point and being able to infer an elevation. So we move from having a static model at 25 metres, which is the average of this tidal area over the last 30 years, to an annual model based on Sentinel-2 data, which is 10 metre resolution. And you can see straight away the detail that you can pick out here compared to the original NIDAM model. So now we have a new product. We have an integrated model. We have Sentinel-2 and Landsat data, which is the first DEA product to actually integrate these two into a sort of operational product. It's modelled relative to sea level at 10 metre resolution, and we have an accompanying uncertainty layer as well too. So it means it's far more easily integrated into other surveying data. We can show confidence of where this model has worked, and in some areas, sometimes the tidal modelling isn't as good as it is in others. Still, with these global tidal models, we can reflect that in the uncertainty. We've done a bunch of validation on this data as well, primarily based on what it is, elevation data. We're using LiDAR data in this instance, acquired off about 500 coastal sites, leveraging what we manage within GA through our elevation portal. And we're getting an absolute error of about 0.27 metres across all of these different tidal regimes. Obviously, the correlation is a little bit weaker in these macro tidal areas because that range is a lot smaller. But I guess the key fact is, if we're looking at aerial LiDAR data, this was acquired up in the Gulf of Carpentaria. This was part of a Northern Territory project that we were collaborating on. This costs a lot of money to go out and fly. You have to go out there to remote areas. You have to plan your survey. You have to hope that you can fly this at low tide and pick up the data you want. This is thousands of dollars worth of data. We can produce a DEA intertidal elevation model, which is broadly comparable in a lot of these regions for a fraction of the cost. This is hundreds of dollars, if not tens of dollars, to run this little area with this model. And we can actually pick up, if you look here, due to those vagaries of doing LiDAR where you have to fly at low tide, we can actually pick up more of the low tide and intertidal zone in many cases because we can actually isolate that. So this is a great cost saving for doing this type of work and characterising this environment. And we now have a time series. So we've been able to pick up how these, we thought these places would be dynamic. We were actually amazed at how dynamic some of these areas are. So we now have an annual time series data that we can start looking at how these shifting mudflats and sandbanks behave over time. So if we jump back to our problem area, this is where one of the areas where coastlines was admittedly quite rubbish. It still looks bad, it's the same image. So we're trying to derive a shoreline here. What kind of change is happening in this environment? We're not getting a lot of information out of coastlines. And when we look at those coastal change points, same type of deal. We only derive coastal change points where we're confident. We're not confident for much of this area. So this isn't going to really inform any kind of change management or coastal monitoring. Within this area now, though, however, we can pick out quite detailed elevation data in annual steps, which means we can start doing things like differencing. So we can start looking at what the elevation of this area was in 2016. 6 years later, we can see there's been significant sediment elevation change, so we can start inferring sediment change. So there's been a loss of sediment or an increase in elevation. And because we have this time series, we can really start drilling down. This is quite experimental. We've only just started to work in this space. We can start using things like optical flow vectors, which comes from computer vision, looking at how change both in magnitude and direction. And we can start looking at inferring where this sediment is going and how fast it's going there. So we're starting to get a much more nuanced picture of change in these environments. So we can start matching up with coastlines. So this is where that complementary approach we're going to talk about. So we now have two products. We have DA coastlines, which is really effective in microtidal areas. We have DA intertidal, much more effective in macrotidal areas. And so we're going to now step through a couple of sort of complementary examples and then into some of the use cases that people have picked this up for. So first example is where they both work reasonably well and they contribute to the understanding of it. So this is in the Gold Coast waterways. You can see a shift in the intertidal zone over these 7 years. You can see there's been a little bit of shift in elevation through here, and you can start picking that up with some differencing, for example. Looking at coastlines over this area, lots of different features are highlighted. You can see much more traditional change out in the beachfront there. You can see some areas that used to be, above mean sea level, but have since disappeared. That'll be interesting to Duncan. I'll see if you've got that one in your mix. And you can actually see those areas that are intertidal to see how they're changing above mean sea level as well. And putting these two data sets together gives you a really comprehensive picture of how this environment has changed over time. Now we're going to look at somewhere where one data set doesn't work so well and the other one does, and how they complement each other. So you can probably guess what's not going to work and where it's not going to work. Yes, mudflats, coastlines, doesn't work really well. This is a nice example you picked out because coastlines down here works pretty well. It's not very, so you can actually see in this one picture the two sort of modes of working for coastlines. Again, coastal change points don't give us a lot of information, but when it's matched up with that differencing of the intertidal products, you really start getting a rich indication of how that area is changing over time. And it's nice to see the correlation between the coastal change points and the DE intertidal changes to show that we're picking up similar sort of dynamics. If we were to flip literally to the other side of the country and into a microtidal zone, we've only got over in Western Australia here, we've got a tidal range of less than 1 metre. Even with a 10 metre intertidal product, you're not going to see a lot because that intertidal zone is very small. So, even these little pixels around here, they're not giving any information to you. There's nothing there. Shifting to coastlines, we find out how this area is highly dynamic. So we're talking about hundreds of metres of change over the last 30 years. And because these are high confidence shorelines, we can confidently then look at the rates of change over time. Now, there'll be some links at the end of this presentation for DEA mapped. We can actually interact with the data in this way. You can start seeing that we can have, 5 metres of change per year. We have quite an accurate uncertainty on this, and you can start looking at profiles with a bit more certainty. So now we'll step into a few of our use cases, and these happen at different scales. We talked a little bit about how we've contributed to state of the environment at a broad scale with coastlines. We've worked on another few aspects of government reporting over the last few years. We did a tailored analysis for Grabrumpa to look at the Great Barrier Reef Outlook Report and essentially tailored what we have done with coastlines at a broad scale and started to slice and dice that for the Great Barrier Reef, talking about onshore and offshore, being able to look at different time periods to see whether there was increased erosion, and then those scientists within Grabrumpa were able to sort of infer some changes based on climate drivers and different things. So we can slice and dice this data quite effectively for different users, and this is great for government reporting. We're currently working with the Torres Strait Regional Authority in a slightly different way. They have a very strong focus of having Indigenous communities contribute observations over time based on what they're seeing on their coastlines, and we're working closely with them to see how those insights relate back to DEA coastlines and how they can help us validate this data as well too to feed into their State of the Environment report for 2026. And I think one of those humps we've gotten over, and this is actually very recently, we attended the Coast to Coast conference, is probably our key conference for coastal science in Australia this year. And it made it very clear to us, and it's probably happening for a few years, but industry uptake is very hard to gauge in government because they often don't come to you to talk about the fact that they're using your data, and you find out accidentally through a news article, through a report. At this conference, we were actually made aware of a lot of use cases, and it was clear to us that our products have made that transition from being scientific outputs to foundational data sets, being treated more like an elevation data set that you just use. It's just one of your tools. Talking to people in this conference, this was really a result of having these well-documented uncertainties and being transparent around the limitations of our product. So these aren't viewed as experimental anymore, and they're well integrated into many of these studies. And it's adding value back to government because often these engineering companies are employed to do contracts for local government or state government. So we're having that sort of government feedback through a different mechanism. So there are a number of instances. Here we've got a couple being used up in northern Queensland as baseline assessments. The one down here in Moreton Bay was to essentially use coastlines in a really new way to assess how sand nourishment and backpass was affecting a certain beach. And these are use cases we wouldn't have even imagined they could do, which is really neat as a scientist to see your product getting taken and extended into these areas. Another nice one in Byron Bay, and we've had a number of conversations with this company using the data to basically see how when a sand bypassing event, so I'm not a coastal scientist, so I'm just going to explain it in my terms, a bunch of sand comes around the point and starts affecting the beach profiles, you can actually use our coastlines data to see how that temporarily, in a temporal fashion, how that affects that beach profile and see the nature of that event. And these are not ways that we imagine our data getting used. And we've been contacted recently by a company called MMA Offshore, who's working as part for the Australian Hydrographic Office, looking at doing bathymetric surveys up in the Kimberley, up in the Buccaneer Archipelago. Finding it really hard to plan up there because of the lack of tidal information, and they're starting to utilise our products to more safely plan their surveys. And this is having a reciprocal effect for us because if they acquire data over these areas, they can provide it to us and feed back into the validation for these remote areas. The last section I'm going to talk about is a bit about our international applications. So we're a big fan of open source workflows. We provide all of our workflows out there. People can grab them and run with them. We've started to work very hard to make them accessible based on data sets that are outside of Australia. We're using what's called the STAC API, which is a spatial temporal asset catalogue, which enables you to query any set of EO data. So mostly in a data cube format. So in this case, we're using Microsoft Planetary Computer. And these are a couple of test runs. Anyone that's flown into South Korea, into Seoul, has probably seen some of these amazing mudflats through Incheon out near the airport there. We wanted to run it on there simply for, we wanted to see how it worked, and it worked really well. And this is over in Washington State in the US, and you can see the detail that we can pick out. This is not using our Australian data, and this is running purely on open source code. So it makes it a really flexible workflow that people can just pick up and run with now. We've had a number of examples of international uptake over the years. This is probably earlier in the piece. This came about, we've been involved in a CEOS Coast, which is an international initiative to sort of help spread Earth observation products and data. And one of those projects was to assist what was a relatively new program at DEA Africa to integrate our Digital Earth Australia coastlines workflow into the African continent. So collaborating with that program and in-country scientists in Africa, we're actually able to help stand up the same capability on Digital Earth Africa, and has become one of their core products as well too. And some of the insights you get from these data sets overseas, we think we have coastal change problems in Australia. Well, this is nothing like some countries overseas are dealing with, and it's really exciting and kind of scary sometimes to see the kind of issues they're dealing with in terms of coastal management. We were actually contacted by a group in San Francisco who'd done what we hoped they would do, picked up our workflow and run it in San Francisco Bay. And you can see this is their work, so we've got a different colour scheme going on. But without our assistance, without our knowledge, they're able to take our workflows, run that on a stack of data, which is a real testament to my team in the way that they've been able to document and make that data, those workflows usable. They contacted us to find out, a few details about the process, and it's really led to a suite of collaboration opportunities. They're looking at sediment movement. We want to build workflows to incorporate local tide data, which is really challenging in estuarine environments where global tide models don't work. And we can evaluate the performance of our workflows with USGS data, which is a really key thing for us in the Landsat Next program. And our last example, we're working as part of the Marine Resources Initiative. So this is a Australian government initiative being coordinated through our Marine Georegulation team. Essentially, it's working with Southeast Asian partners to capacity build. So we want to be able to provide capacity for these different countries and governments around Southeast Asia to implement some of our coastal products. So we've participated in workshops over in the Philippines, and in its early stages, seeing implementations of these different kind of data sets and workflows that we've designed, working in the Philippines, Vietnam, and now into Indonesia. So these are my last two slides. I kind of wanted to, it's often par for course to talk about future directions, and there's a lot of different sort of experimental work we could put up here, but what I decided to do was talk about the fact that our future directions are more and more hinged on how we collaborate in this space. We're fortunate to have a range of stakeholders that we've talked about, but programs that do this kind of stuff that, as I said, are complementary. For example, the one I put here of CoStat, this is an instantaneous shoreline mapping capability where people can map shorelines to look at impacts. We've got people down in Victoria which are integrating our data with drones. We've got people in Western Australia which are trying to supplement their aerial photogrammetry with our data. So this kind of data and knowledge sharing has been crucial to the development of our products, but it's also going to be crucial to what we do next, because we need to know that, you know, the directions we take, the tweaks we make, the different data sets we integrate, whether that be further experimental with optical data, looking at things like SAR, are applicable to the community. So I guess future directions, you can hypothesise about what we're going to do next, but we will really want to make sure that we're part of this community and that we're doing things in a way that is going to be useful to everyone. And I think that's cyclical. People feed back on that, and we've got a very good relationship with these stakeholders. Final slide. When you get to these key messages, you don't want to make them too complex, but I found out I had a lot of things I wanted to say. So I guess at the top level, Earth observation data as a takeaway is a powerful means of doing this kind of stuff. You can do this at continental scales, you can do this at local scales, and it really gives you that power to do this vast range of reporting and monitoring. Geoscience has really set us up in such a good way for this, and it's interesting that Stuart's in the room here. This is totally by accident, but some of this work that we pioneered back in the day of getting this data into these kind of frameworks has been really key to us unlocking the potential to do these kind of applications. And that kind of stuff is translated to initiatives across the world as well too. Integrated and complementary approaches are key to addressing this. So whether it's complementary data sets we design, or whether we do that in concert with collaborators, that's a crucial part of this. Transparency. I guess in Earth observation data, my observation through the time I've been working here, we had a tendency to sort of overpromise and tell people that, you know, our product would solve all the world's ills and that it's the best thing. I think an increasing transparency with stakeholders about product limitations, where things don't work, and being upfront with that actually generates more trust. People then know that what you're saying they can trust, and it actually fosters collaboration opportunities. And then just to go back on that last point, because it's our main point, is open source data. These things need to be open source. Science needs to be open source, because it means not only do we have that collaboration, it means they can be adopted and adapted well beyond their original scope. And this just drives impact for everybody. That's me. Sorry, it went a bit long, but thank you very much for your time.